ring. Whenever I wanted a good view of the site, and especially the reactors, I climbed to the top of the Goliath. Its bridge is about as high as Nelson's column. We're passing now over number 2 reactor. Within number 1 reactor vault, standing on the floor raft, is a concrete plinth on which the vessel is supported. You can see part of the insulation fitted to the inside wall of the vault. When the reactor is working, a stream of cooling air is passed between the vault wall and the inside faces of the plates to maintain the concrete at a reasonable temperature. The vault walls are of dense concrete, about 9 feet thick, and form a radiation barrier. It is commonly referred to as the biological shield. Well, we successfully installed the bottom ring section, and it was felt at last that we were getting away from what seemed a predominantly civil engineering site. Things appeared to be going smoothly at Bradwell. The second boiler arrived in the estuary absolutely on time. We had plenty to occupy our minds without worrying about the outside world. The second ring of number 1 vessel was installed in August 1958. The ring is pierced by 6 large apertures, to which will be welded the inlet gas ducts associated with core cooling. By the time we had erected 3 boilers, all on the north side of number 1 reactor, clean conditions had been achieved within the first one, and tubing up operations were in progress. All the tubing, except the superheater banks, is of the integral finned type. Before dispatch to site, the tubes are tested ultrasonically to ensure that none of the welds will fail in service. On site, they are cleaned externally by a shot blasting process prior to being inserted in the boilers. At the base of each boiler is a horizontal cutout to permit passage of the cleaned coils. The coils are hoisted into position by an internal winch and are stacked in a stepped pattern for maximum heat transfer efficiency. Hot carbon dioxide gas from the reactor core flows over the tubes from top to bottom of the boiler at a pressure of nearly 140 pounds to generate steam within the tubes. The ends of the tubes pass through holes pierced in the boiler shell to connect to external steam drums and headers. By the late spring of 1959, we had installed all the ring segments in number 1 reactor pressure vessel, with the exception of the top dome. This part of the vessel, on which the welders are now working, is 4 inches thick and contains a large number of openings for standpipes. It is through these that control and fuel handling equipment will operate. Looking back on the construction of Bradwell, there have been many incidents that cling to one's memory. The reactor building emerging above ground level, the first boiler lift, getting people to work together as a coordinated team. But perhaps my most outstanding memory was the lift of the top dome. In this film, all things appear smooth in operation, like a well-oiled clockwork mechanism. Snap your fingers, and a giant crane automatically installs a heavy item of equipment. We had suffered a delay on the top dome lift that had thrown us back several weeks on our program. A stage had been reached where associated work on the reactor would be seriously hindered, in spite of all the careful programming, if the dome was not installed. There was a tension on the site. It affected most of us. It was one of those days we expect but seldom get in June, when the Goliath came trundling down its tracks with the top dome slung high. The secondary shielding walls which separate the boiler houses from the reactor operating floor had almost reached their full height, and all 6 boilers had been installed. It was over these structures that the 200-ton top dome had to travel. There's a good view of the reactor vessel in its vault, complete but for the top dome. And at last, the dome in position. We were relieved to see the successful completion of the vessel, and we could now start the business of pressure testing, stress relieving, and internal cleaning. These inlet apertures in the vessel allow the carbon dioxide coolant gas to recirculate through the core after the gas has given off its heat to the boiler tubing. Each boiler has its own circuit and gas circulator. The ducting, which is 5 feet in diameter, passing through the biological shielding to connect to the outlet end of the circulator. The circulators are located one directly below each boiler. They are single-stage axial flow units driven by squirrel cage induction motors and designed for normal operation over a speed range of 600 to 3,000 RPM. The uranium fuel in each reactor is handled by a multi-purpose charge-discharge machine. Now that the vessel was complete, we could install the 2 gantry girders which support this machine. After the top dome had been fitted, we had been able to lift and position the thermal dome. This hemispherical steel structure rests on top of the biological shield and, like the top dome, is pierced by apertures to allow the passage of fuel and control rods into the reactor core. Some while later, on the reactor operating floor above the thermal dome, the standpipes are being fitted. These are guide tubes through which the charge machine passes uranium fuel into the reactor. Some of them are used for the control rods that control the reactor. There will be 256 standpipes when finished. They pass through the thermal dome and link up with the openings in the top cap of the reactor vessel itself. With the welding completed on number 1 vessel, it was stress relieved by a system of internal electric heaters. Attached to the vessel are hundreds of thermocouples which record the temperature rise and fall over the whole surface and transmit their readings back to a system of recorders at a central control point. By this means, a graph can be produced which shows how each small section of the vessel behaved during the heat rise and during the cooling, which is allowed to happen naturally afterwards. These tubes contain the heaters, which will raise the vessel to a temperature of approximately 600 degrees centigrade. Later, the vessel was pressure tested pneumatically to 260 pounds per square inch. Now that the top cap was on, things were moving fast. Perhaps the most arduous task within the reactor vessels was the establishment of clean conditions. The interior walls had to be flame cleaned and wire brushed to remove all dirt, scale and foreign matter. Such incompatible materials have an adverse effect on the neutron absorption and hence reactor power. The inside of the vessel and all equipment used were coated with a colloidal graphite compound, and the cleanliness achieved was the equivalent of a hospital surgical room. Graphite blocks had been arriving on site for some considerable time and have been stored in sealed containers in a temporary air-conditioned building on site. The graphite core in each reactor weighs approximately 2,000 tons. It is made up of individual graphite bricks.